This is Algebra 2, Lesson 5-1, Polynomial Functions. A monomial is an expression that is a real number, a variable, or the product of real numbers and variables. For example, you could have something like x, 2x, or 12xy. They cannot have any positive or plus or minus signs between them. The degree of the monomial is the exponent of the variable. Okay, for example, if I had 3x to the fourth, the degree of that polynomial would be 4 because the variable has an exponent of 4. A polynomial is a monomial, or the sum of monomials. For example, 3x to the third plus 2x minus 9. That's a polynomial. It happens to be a polynomial of degree 3 because the largest variable of any, largest exponent on any one variable is 3. A binomial is a polynomial of two terms, like 2x plus 3. A trinomial is a polynomial of three terms, 4x to the third plus 5x minus 9. The degree of the polynomial is very similar to the degree of the monomial. It's the greatest degree among monomial terms. So you find the monomial that has the highest degree. That's the degree of the monomial, but it also becomes the degree of the polynomial as well. Standard form of a polynomial is writing a polynomial so that the variables are listed in descending order by degree. I've written all of the above polynomials in standard form because my brain works in standard form. Standard form means if I have something to the fourth power, like 3x to the fourth, that would come before negative 2x to the third, which would come before 7x squared, which would come before like 4. Because we went from 4, 3, 2, we didn't have anything that was to the first power, and then none. A turning point is a place where the graph of a polynomial changes directions. And the end behavior is the direction of the graph to the far left and the far right of a polynomial graph. And I'll show you some pictures of that in just a few minutes. All right, the degree of a polynomial equation provides information about the end behavior, turning points, and number of solutions for the polynomial function. You can determine end behavior and turning points from the degree of the polynomial. So you want to always pay attention to the degree of your polynomial. You can classify a polynomial by the number of terms it contains, and you can also classify it by its degree. The names assigned to each degree are listed below here. Okay, so we have the degree. Okay, we have examples of each one of these. For example, anything to the degree of 0 is called a constant. It's any number, like 2, 3, negative 4. It only has one term, and it's a monomial. If it's linear, it's to the first degree. Degree of 1 means like x plus 3. The exponent on the variable is a 1, and we imply that. We never write out x to the first plus 3. This particular polynomial has two terms, so it's a binomial. If it's squared, if it has a degree of 2, otherwise known as squared, it's a quadratic. We've been talking about quadratics. Okay, in this particular case, 3x squared is a quadratic, but it only has one term, so it's a monomial. If it's to the third power, it's cubic. 2x to the third minus 5x squared minus 2x. That has three terms, so it's a cubic trinomial. If it's to the fourth power, it's quartic. X to the fourth plus 3x squared. Number of terms there is 2, so it's a binomial. If it's to the fifth power, it's quintic. Negative 2x to the fifth plus 3x squared minus x plus 4. That happens to have 4 terms, so we just call it a polynomial of 4 terms. Once you get past trinomial, you don't have special numbers. And pretty much once you get past quintic, you just have a degree of 6 or a degree of 7 or a degree of 8. All right, now, we're going to write each polynomial in standard form, and then we're going to classify it by its degree and the number of terms it has. So here we have number 1 is 9 plus x to the third. X to the third is not 9 plus x to the third is not written in standard form because we need to have the variable coming, the largest degree of the variable coming first, because you want to write them in descending order. So x to the third would come before x to the second, which comes before x to the first. We have no other x's, so x to the third comes first, and then it's plus 9. It is 2 terms, so this happens to be a cubic binomial. Number 2 here, x to the third minus 2x squared minus 3x to the fourth. It's close to being in standard form, but the negative 3x to the fourth needs to go to the beginning, and sign goes with numbers, so it becomes negative 3x to the fourth plus x to the third minus 2x squared. It is 3 terms, so it's a trinomial. It's to the 4th power, so it's quartic. So it is a quartic trinomial. Number 3 here, 6 minus 2x to the 5th, negative 2x to the 5th plus 6 would be in standard form. It is 2 terms, so it's a binomial. It's to the 5th degree, so it's quintic. So this is a quintic binomial. And you have to learn these terms because they are very important, and you'll learn and you'll use them throughout the rest of this year in Algebra 2 and in other math classes as well. Now the end behavior describes the graph at the far left and the far right. Okay? A turning point is where the graph changes directions. You can determine end behavior and turning points from the degree of a polynomial. For example, I gave you this lovely polynomial that looks like a funny looking W. The blue circles are your turning points and the pink circles are your zeros. Zeros are where the graph crosses the x-axis because x is 0 at that, or excuse me, y is 0 at that point. And your turning points are where what happens as your graph is going decidedly making a change of direction. Okay? So it's easy you can determine your end behavior and your turning points from the degree. If your degree is odd, you will have an even number of turning points. If your leading coefficient a is greater than 0, it will end down and then up. If a is less than 0, it ends up and then down. If your degree is even, you have an odd number of turning points. If a is greater than 0, both ends are up, and if a is less than 0, both ends are down. So with this particular graph right here, this W-looking graph that I have here, I have 3 turning points, so I have an odd number of turning points, which means it's of an even degree. And both ends are up, which means we know the leading coefficient in front of the first term is got to be positive. Okay? So let's take a look at some other things. In general, the graph of a polynomial function of degree n, where n is greater than or equal to 1, has at most n minus 1 turning point. So in other words, it has 1 less turning points than it does its degree. So if it is a 5th degree, it's going to have 4 turning points, at most 4 turning points. If it's a 9th degree, it's going to have at most 8 turning points, etc. The graph of a polynomial function of an odd degree has an even number of turning points, because there's always 1 less. The graph of a polynomial function of an even degree has an odd number of turning points. So let's take a look at this. Consider the leading term of each polynomial function. What is the end behavior of the graph? So if we're looking at this, we have 3x to the 4th is my leading term right here. Okay? A is greater than 0. I know that because 3 is greater than 0, and it's to the 4th degree. So from that, I know that my degree is even, so I will have an odd number of turning points. Okay? And I know my a is greater than 0, so I know it's going to end up and up. Okay? So what is the end behavior of the graph? The end behavior of the graph is up and up. So in other words, it's going to be looking like the graph goes there and in one direction, it could look like that. Okay? It can have at most 3 turning points, and this one would have 3 turning points, 1, 2, and 3. Okay? If it had turning points, it would have this would be a turning point, this would be a turning point, and that would be a turning point. Okay? So the graph looks something similar to that. All right, number 2. Y equals negative 4x to the 3rd plus 2x squared plus 7. This is a 3rd degree. Okay. A is less than 0. So it's an odd number of degrees. Degree is odd. So it has an even number of turning points. And A is less than 0, so it ends up and then down. And you have to pretty much memorize the end behavior. So the little chart that I gave you next to the polynomial function with the graph, you need to memorize that. There's no other way around it. You just have to memorize it. That's the only way you're going to get really good at it. So in other words, this graph is going to look like this. It ends up and then down, so your graph's going to look something like that. It may not, but it could. Okay. All right, so graphing a polynomial function without using your graphing calculator. because we can all put things in our graphing calculator, get the graphing calculator to graph it for you. However, you know me, I'm going to force you to graph it by hand as well. So it's really important that you understand how to graph by hand. The easiest way to do that is make a table of values to help sketch the middle part of your graph. Use what you know about the end behavior to sketch the ends of the graph. So if I have the graph y equals negative x to the third plus 2x squared minus x minus 2, I'm going to make a little table of values. Okay, I'm going to extend this up a little bit so that I can actually see it. I'm going to use it below it here. So I'm going to have a little table of values. Table of values just means I have an x and y table. Okay? And I'm going to put in numbers. I'm going to put in like negative 2, negative 1, 0, 1, 2, and maybe go to 3. So who knows what I'm going to do here. All right, so I'm going to make a table of values, and I'm going to plug things in. So if I just plug the numbers into my calculator, okay, the opposite of negative 2 cubed, okay, now basically all you're doing is plugging negative 2 into this function right here and getting the answer. So if I plug in negative 2 in for x, I get 16 for y. If I plug in negative 1 for x, I get 2 for y. If I plug in 0 for x, I get negative 2 for y. If I plug in positive 1, I get negative 2 again. If I plug in 2, I get negative 4. And if I plug in 3, I get negative 14. Now, I probably can't fit all of those points on my graph, but I can fit at least a few. Okay, now, it's a third degree. Okay. So we know it has at most 2 turning points, because it always has one less turning point than it does degree. Okay, so it cannot have more than 2 turning points. A is less than 0, so it goes up then down. Okay. So my turning points, okay, if I was to do my turning points, it looks like my turning point is going to be somewhere, at least one of my turning points I can tell is somewhere around, okay, between these numbers here, because they're the same number. Okay, that tells me something's going on here. So, if I plugged in numbers between those, okay, I could probably figure this out. So I'm just going to plot in what I do know. So I'm going to plot some x and y axes here. Well, I think I can just go straight in the middle. So let's go x-axis here, y-axis there. This is my x-axis, this is my y-axis. I'm going to plot the points negative 2, 16. Not sure I'm going to be able to get that on there, but I can definitely get negative 1, 2 on there. So negative 1, 2 is here. I can get 0, negative 2, that's there. I can get 1, negative 2, that's there. I can get 2, negative 4, that's there. 3, negative 14. 4, 5, 6 is going to be way down here. So I at least know that my graph looks a little bit like it's doing this. It's not a very great. There we go. It's a little bit better. Okay. It's a little harder to sketch these. So my graph looks something like that. That gives me an idea of what my graph looks like. Okay. So it has at most 2 turning points. Now, if I wanted to find out exactly what those turning points were, then I would put this on my graphing calculator and find those exact turning points. Okay. So my turning points then, now I'm going to put it on my graphing calculator. And when I do that, I can see where the graph is turning, and I can ask it to find that point. It's not an intersection. Remember, it's like a maximum or a minimum. So if I was to add this graph to my calculator, I would just add negative x to the third power plus 2x squared minus x minus 2. If I graph that. Okay. Then if I want to figure out where my turning points are, it looks like 0 for x is one of my turning points. So that's only obvious. Okay. But I need to know what the y value is for that. So I'm going to calculate it. So I'm just going to go to menu, and we're going to do analyze graph. And I just want to figure out, I don't want to figure out its zeros. I kind of want to figure out, it seems like it's minimum. Let's call it a minimum. small little slice of that graph. And if we do that, we find that it is at, looks like negative 0.333, in other words, 1/3, and negative 2.15. Okay, so my turning points then are at 1/3, 1/3, and negative 2.15. That's one turning point. The other turning point, if I have to find that one, okay, because here's the one turning point looks like it's somewhere around here, and the other turning point looks like it's somewhere around there. So I need to figure out what those 2 points are. So I'm going to figure that out. So now I'm going to hit my menu again and analyze graph a second time, and I'm going to hit maximum because it seems like it's going to be going down from there. So I'm going to scroll. So I grab part of the left-hand side of that, scroll to the right. If I look there, it looks like that happens to be at 0, -2. Okay, so it's right at a point. So my turning points are 1/3, negative 2.15, and 0, -2 is my other turning point. So there's my 2 turning points. The last thing it asked me to do is describe the graph, including end behavior, turning points, and increasing, decreasing intervals. What that means is, what is my graph doing? Okay. If you look at it, it's decreasing. Okay, from here to here, it's decreasing. Basically, it's because this can go up forever because of the arrowhead. It's decreasing from negative infinity to about 1/3 because that's when it's going down. So it decreases from negative infinity to 1/3, and then it increases from 1/3 to 1. And then it decreases again from 1 to infinity. So there we go. We've answered all the questions they asked us to do, and I didn't have to graph it on my graphing calculator first because you do have to know how to do it. Okay. Obviously, if this was a hand problem, I wouldn't ask you to give me the turning points. I would just ask you to be able to give me approximately where the turning points are. Okay. Let's take a look at this second graph. Y equals x to the third minus 1. Okay. So let's make another little table of values. I think I'll do it in purple this time. So let's do a little x and y chart here. I'm going to stick with -2, -1, 0, 1, 2, 3. They give me approximate good answers. If I put in -1 cubed is -1 minus 1, excuse me, -2 cubed, sorry. -2 cubed is -8, minus 1 is -9. -1 cubed is -1, minus 1 is -2. 0 cubed is 0, minus 1 is -1. 1 cubed is 1, minus 1 is 0. 2 cubed is 8, minus 1 is 7. 3 cubed is 27, minus 1 is 26. So I'm obviously not graphing that point. Okay. Once again, I can draw my axes in. So I'll draw my axes in. Okay, so there's my x and y axis. There we go. That's not where it's supposed to be. All right, so I'm going to graph. Okay, well, let's look at this. Turning points at most 2 because it's an odd degree. Okay, so we have an odd degree at most 2 turning points. A is greater than 0, so odd degree A is greater than 0. End behavior is down then up. So down, then up. All right, so let's graph this. If I have -2, -9, 1, 2, 3, 4, 5, 6, 7, 8. Oh, just barely off the graph right there. And -1, -2 is there. 0, -1 is there. 1, 0 is there. 2, 7. 1, 2, 3, 4, 5, 6, 7 is there, and the rest of it's not going to go on there. So it looks like it's looking something like this. Okay? There's no definitive turning points. A turning point means it has to be changing direction. And it really isn't changing direction. It's going up. It's just going up quickly, then it slows down going up, and then it goes up fast again. So there are no turning points. And it increases from negative infinity to infinity. So there we go. So that's graphing those. All right, now, this last thing is a little bit interesting. Suppose you're given a set of polynomial function outputs. You know their inputs are an ordered set of x values in which the consecutive x values differ by a constant. By analyzing the differences of the consecutive y values, it's possible to determine the least degree polynomial function that could generate the data. Not that does generate the data, but that could. If the first differences are constant, the function is linear. If the second differences, but not the first, then the function is quadratic. If the third, but not the second, then the function is cubic, and so on and so forth. So let's take a look at this data right here. Okay, what is the degree of the polynomial function that generates the data shown? All right, first things first, I like to just look at my y values. So from 52 to 18, and then from 18 to 2, and then from 2 to negative 2, and then from negative 2 to 0, and then from 0 to 2, and then from 2 to negative 2. Okay, so 52 to 18. So if I went 18 minus 52, because I'm trying to figure out what the difference is. So from 52 to 18, we had to subtract 34. From 18 to 2, we have to subtract 16. From 2 to negative 2, we actually subtract 4. From negative 2 to 0, we actually add 2. From 0 to 2, again, you add 2. And from 2 to negative 2, you subtract 4. There are no constant differences between those values. So now I'm going to look at, and I'll do it in a different color, the differences between these. Halfway through. All right, so from negative 34 to negative 16, we actually add 18. From negative 16 to negative 4, we actually add 12. All you have to do is negative 4 minus negative 16. Just make sure you keep all your negative signs constant. And you're basically subtracting the second number from the first number. For example, negative 4 minus negative 16. That's plus the opposite, so that's how I get 12. To go from negative 4 to positive 2, we're actually adding 6. From positive 2 to positive 2, you're adding nothing. From 2 to negative 4, you're subtracting 6. So still no constant difference here. Let's go to the third one. 18 to 12, 12 to 6, 6 to 0, 0 to 6. To get from 18 to 12, I'm going to subtract 6. From 12 to 6, I'm going to subtract 6. From 6 to 0, I'm going to subtract 6. And from 0 to negative 6, I'm going to subtract 6. Ah, we finally have a constant difference. The constant difference, okay, this was my first set of subtractions. This was my second set of subtractions. This was my third set of subtractions, which means this could be a third degree or cubic polynomial function. Okay, could be a third degree or cubic polynomial function. And here we have what polynomial functions. This is the beginning of polynomial functions. We'll be doing an awful lot with polynomial functions as this chapter progresses.